For a difference, today we would like to start on time because we have a very busy schedule. First, we have a guest that gave the ITC colloquium, Gianfranco Bertone, over there. Always inspiring to listen to him, and he will tell us a few additional things now. But before I get to the program, I just wanted to welcome the prospective students that are here. Because they represent our future, and we hope that they will make the discoveries that my generation of scientists failed to discover. So they are sitting all around us, and it's great to see them, and I hope they will all come here. I also wanted to mention the other talks we have today. We have another visitor. So first, Gianfranco will. He's at the University of Amsterdam, originally born in Italy. So he has a very good DNA. Astronomy is pretty much started over there with Galileo Galilei. And he will tell us about Global Cosmos Prize program for science literacy. That's a very important initiative. Gianfranco is involved in promoting education. In southern Italy, where he was born. Then we'll hear from Andy Burkert. Where is Andy? Andy should be here. Yeah. Oh, over there. Yeah. Great to see you, Andy. He comes here every year, and we love to listen to him. Always new insights. And today he's located most of the time at LMU in Munich, and he will tell us. He would ask a question: are there no missing baryons in massive spiral galaxies?
Well, you know the answer as usual.
But aren't we living in one? Or are you telling us that the Milky Way doesn't have mass?
Well, wait till I tell you.
Oh, okay. Well, that would be interesting. I mean, of course, it's reassuring to learn that all the matter in the universe is what we are made of, but most of us gave up on that for a while. So we'll hear. In fact, Charles was searching for. Yeah, right. Anyway, we'll see. We'll see. And then we'll hear from Jung-Tsung Lee from Ohio State University, over there, who will tell us about what solar disk gamma rays tell us about galactic cosmic rays and solar magnetic fields. Nothing controversial about that. And then Roger de Belsunce, did I say it right? Yeah, from MIT will tell us about high-redshift cosmology with the Lyman-alpha forest. And today we have 5 speakers, so I would like to ask all of them to be sort of concise within the 10-minute time limit, because the 5th speaker was originally scheduled a month ago. There was some confusion, so we are accommodating the 5th speaker today. So we will hear from Natan de Isídio from ISO. Where is Natan? Oh, behind me. Who will tell us about the kinematic imprinting of environmental quenching in nearby galaxies. A very interesting program today, so let's keep on schedule and start with Gianfranco. Yep.
Should we use the microphone or is it?
Yeah. Okay, so you should stand behind anything you say.
All right, so I'm putting my science communication hat now after the colloquium. And I want to tell you about this new initiative that was recently endorsed in by the International Decade of Sciences for Sustainable Development. The starting point for this was something you're familiar with. You know, the idea that science literacy is today more important than ever, and it is so at the individual level for informed decision making and to protect ourselves against misinformation. But it's also important because it opens the path to high-skilled occupations, and this is something which is really essential for the knowledge-based economies like the ones we live in. But there's also the fact that poverty and disadvantaged social background, they remain huge hurdles on the path of scientific literacy. And this is something that you can see across countries and across data sets. So as Avi said, I work in the Netherlands. I've been there for 15 years, where we started this GRAPPA Center for Gravitation and Natural Particle Physics. If you look at the fraction of 18-year-old kids that have a non-Western background, they're 51% of the overall population in Amsterdam. If you look in high schools, and in particular the kind of high schools that lead to research, open the doors for research universities, that percentage drops to 26%. If you look inside the UvA, the University of Amsterdam Science Faculty, this drops to 10%, and in physics and astronomy, the percentage is even smaller. And you know, I could mention many other kind of evidence that shows this. For OECD countries, you know, the number of students for high-status families that obtain university degrees compared for the low-status families. This is true in the UK. This is true in the US, and so on. But since I don't have much time, you know, I think it's not worth spending time on this. I think this is something. I think we have very strong evidence for this. I think this is really non-controversial. So this was the starting point of a reflection on, you know, centering around this question. How can we engage students at an early age to widen access and participation and to promote scientific literacy? And so to address some of these issues, I launched an initiative in my hometown in the south of Italy. And the reason why I decided to do so there is that if you look at this is one of the poorest regions and underdeveloped regions of all of Europe. Just look at the youth unemployment map. In Europe, you will see there in the south of Italy, and in particular in Calabria, this goes above 25%. Specifically in the city I was born in, this is of order 50%, actually. Okay, so I thought that this would be like a nice place to start, and you know, this is where I could have most impact. So I started with the following goals. The first one was to promote critical thinking and scientific culture worldwide through the reading and discussion of outstanding science outreach books. So we decided to center everything around slow science, which I thought, and I'm happy to tell you more if you're interested, but we thought it was an interesting angle, especially when working with schools. And the other goal was to recognize and celebrate scientists and science writers who effectively engage the general public and improve the public understanding of science. So in practice, we give 2 prizes every year. The one is called the Cosmos Prize, and it's assigned by a scientific committee composed of internationally renowned scientists. Another one is the Cosmos Students Prize, which is independently assigned by an assembly of hundreds of high school students through a system of student juries that are activated on the national territory. And the starting point is a short list of 5 books that we send them. So we ensure that the quality of the books they read is very, very high. These are the prizes we give them. We collaborate with artists. This is an American artist who created these sculptures for us. This one was created by a local artist, and one of the winners of this prize is actually Avi Loeb, who came all the way to Calabria to engage with the students. This is another event that happened more recently in the Netherlands. I'll briefly tell you more about that as well. How does this work in practice? So this starts with us prompting publishers to send to a selection committee to us a long list of books. Out of those books, we select 5 books that we send to schools, 5 schools that we send it to a scientific jury. The schools, they engage in debates among themselves and with the authors, and then they come together in a general assembly, and then they award their own prize, the Cosmos Students' Prize, and the jury independently gives the more senior, let's say, prize. Now, since I started this initiative, I started thinking about this in 2018. The initiative was very successful, beyond my expectations. And in fact, now we have parallel initiatives in several different countries. We have it in, not just Amsterdam, but in the Netherlands. In France, we meet in this beautiful Institut de France in the center of Paris. And now we're going to have the first pilot edition this year on the Canary Islands in Spain. Why does this work? It works because it's really a virtuous cycle. The authors, they gain visibility and impact, and I must say also they love the contact with high school kids. Publishers, they manage to sell more copies. Students learn, and they get via a series of tailored incentives. We have to tailor incentives to different countries, as a matter of fact. Schools, they gain high-impact science literacy programs. The teachers, the sponsors, and especially the communities, they can strengthen the link between science, education, and society. Now, recently, this initiative was endorsed by the IDSSD. For those of you who are not familiar with it, just a few years ago, the United Nations General Assembly declared the decade 2024-2023 as the International Decade of Sciences for Sustainable Development. And if you look at the language they use, the way they present this on the official website, it offers a unique opportunity for humanity to fully harness the power of science in advancing sustainable development and securing a safe and prosperous future for everyone. So all the member states are urged to actively back the decades. And just a few months ago, this Global Cosmos Prize was officially endorsed by the IDSCD. So this is an initiative that is, that was proposed by the United Nations, and UNESCO is actually in charge of leading its implementations. What are the next steps? So we want to scale this program to up to 20 countries by 2028. The limit is actually how much we will be able to do. There's a lot of interest. We receive a lot of interest from many colleagues worldwide. We're trying to find a way of making this feasible and sustainable, also in view of the limited time and resources we currently have. The goal is to engage tens of thousands of students, really worldwide, in reading and debating outstanding popular science books. We already awarded 1,000 students for each of these initiatives, so this goal seems realistic. We're setting up a central, lightweight digital hub, and the idea there is to support those who want the local committees who want to set up a national program and make sure we align the goals, that whatever they do is aligned with the goals of the global initiatives. And then what we want to try and do, this has proven to be quite difficult, but at least we have 4 examples where it actually works. We want to help national committees to self-finance the initiative and to train them to fund the initiative through institutional support, philanthropic grants, and corporate sponsors. Every country is different. In particular, the incentives that we need to offer students to involve them in these initiatives depend on the specific school system. If you're interested in organizing a national initiative, be it here in the US, the main difficulty here in the US is that there's no centralized school system. We usually work directly with the Ministry of Education. Here there's no such thing, so it's proving quite difficult to get started. But if you have ideas, or if you want to get something started, be it in the US or somewhere else, please see me after the talk or contact me at this email address. Thank you.
Thank you so much, Gianfranco, for organizing this. Because the older I get, the more I recognize that science is better than politics. I mean, it's not just because the people doing science are more interesting. It's because science is based on cooperation. and politics very often on bringing people apart from each other. And so, so it's really important, perhaps the younger generation can bring a better future, and that's what you're doing with engaging with students and promoting science. So thank you for doing that. And let's hope, I mean, CERN was established with the vision back then that science would bring the European countries together. That was within Europe, but we can globalize it. That would make much more sense. So, thank you. Questions, comments on what we heard? Yes, please.
Do you have any stats on the actual change in student outcomes from these different communities?
Yeah, that's something we're working on. It's very difficult. You know, this is in general true for science outreach. All I have for the moment is kind of anecdotal evidence. So many of the kids that were involved in these initiatives, for many of them, it was the first time they read a science book, first time they met a scientist. You know, Avi maybe remembers, you know, the energy and the excitement that was in the room when you know, we managed to attract these speakers. We also, and one of the reasons why it's difficult to disentangle the impact is that we also organize around this prize initiative a full-fledged festival of science. So it's very difficult for us to tell, you know, what's most important and what was most important, most inspiring also for the students. I have like a strong feeling that this is making a huge difference and a big impact on the community. We're working on how to make this a bit more quantitative and objective.
Yeah, and Gianfranco is not the only person in this room. He came from southern Italy, Calabria. We have.
I'm from Puglia.
Okay, but still.
Completely different part.
Completely.
After I visited the southern Italy, I went to Milan, which is in the north. It's a different world. I really like the people of the south. They are so much nicer.
I agree.
Let's thank Gianfranco again.
I'm missing the snow. I hope it comes back. You know, it was there last week. I heard, I saw, and came a week too late. Yeah. Well, it's unpredictable now. You know, everything is chaos or emergence. I would say it's emergence. Okay, I want to talk. I'm happy to be here. Thank you again for always allowing me to come. Just want to say this is for me the highlight of the year, because when I get home, I have a whole year to work on all the ideas that come up when I'm here. I want to tell you quickly about a project with Chris McKee, and it is motivated by this kind of mass distribution, basically the density distribution of galaxies as function of their mass, which, as you know, follows the Schechter function, which is rather flat when you have small galaxies. If you look at small galaxies, then there's a transition and there's a deep decline in the number of galaxies when you go to large, massive objects. And if you compare this to the dark matter halos as function of mass, the number density of dark matter halos, you see it's very different compared to galaxies. And the people usually say, here's the most efficient way to form stars in dark matter halos, and actually our Milky Way lies close to here. So for whatever reason, it seems to be a fine-tuned Milky Way. And I want to show you that this is all wrong. Yeah. And the usual answer or kind of explanation for this is that there is a dependence on the mass fraction, the stellar mass fraction to the halo mass, stellar mass to halo mass, or the baryon fraction with halo mass. And it's shown by this kind of curve over there. So when you had small galaxies, then the baryon fraction or the stellar mass fraction is very small, and then it rises as a power law with the power law slope of beta, reaches a maximum close to the Milky Way, and then it declines again when you go to larger masses. And the power law slope is very well determined. You need to be a little careful how you define it. You know, whether you plot here the dark matter mass or the stellar mass, if you look at the mass fraction as function of dark matter mass, the power law for this rise is 4.38. If you want to do it as function of stellar mass, then you have to basically do beta divided by 1 plus beta halo, and then you get a rise of 0.18, and then you have this decline, and the argument has been very simple. When we go to small galaxies, stellar feedback blows out a lot of baryons, and that's why the smaller the galaxy in mass, the less baryons are left to form stars. And here you basically get then the maximum, and then here AGN feedback, the feedback of supermassive black hole begins to disrupt galaxies and eject a lot of mass, and that's why the whole thing is going down here on that side. And this kind of Monster mass function, Barrosi mass function, is used in almost all galaxy models, and it is a test for any numerical simulation where you implement some feedback in order to get your baryons out as a test to see whether your simulation works, and you fine-tune your simulation till you get it right, because nobody can really resolve an AGN. You know, if you have a kiloparsec, it has nothing to do with an AGN, and this is your resolution. Oh, yeah. Okay, I wonder. Anyway, so now there was a paper by Posti in 2019 where they looked at local galaxies, got the rotation curves, measured dark matter masses, and then plotted the stellar mass fraction as function of stellar mass. And they found indeed the rise as expected by Moster, so following this correlation. But then the turnaround didn't occur. Instead, the mass fraction increased all the way till you got the cosmic mass fraction, baryon fraction. And okay, at that time, nobody wanted to take it serious because you had all the subgrid models already implemented. You didn't want to start from scratch new. And there were the arguments, okay, how do you get really the mass of the dark matter right, given the fact that these are strongly baryon-dominated galaxies from the rotation curves, how you then work out what is dark matter. And indeed, there's also only a few galaxies, so maybe it's not worth thinking about this. And then Chris and I thought, okay, wow, let's do a bigger sample, 13,305 galaxies. And we took from Arjen van der Wel the kind of the catalog of Candle's galaxies, which have this redshift range of 0.5 to 1.5. And in the catalog, we get redshift, we get stellar mass, and we get the disk half-mass radius. And now, of course, you might wonder how you get the dark matter mass, but there's a very simple argument for that, which works beautifully well. You all know that dark halos have a little bit of a spin, a specific angular momentum, little j, and it's well known that if you normalize this to the real radius times the real velocity, which is the property at the edge of the realized dark matter halo, then you get a dimensionless lambda value, and this lambda parameter on average is universal. It's a universal constant of 0.035. Of course, it varies from one galaxy to the other, but if you have a large sample, it's like this. And the good part, it's independent of redshift, it's independent of mass. It is like this, and it's a result of this self-consistent or the scale evolution of structure formation in the universe in the cold dark matter scenario. Now you can do the same for galactic disks, and you can define a spin parameter, which is the specific angular momentum of the disk, divided by RV and VV. And if the angular momentum of the gas that forms a disk was gained by the same cosmological gravitational torque, which it has, then you might say, okay, maybe we get a similar lambda disk as we get for the halo. It turns out it's not true in details because, first of all, there are more torques when the gas falls into the disk. And in addition, you blow out gas, and you never know whether there's a selection effect. You might blow out low angular momentum gas from the AGN, or what do I know? But it turns out when you look at observations and when you look at theory, that indeed the mean lambda we'll find is really close to the lambda halo. So this is something which only works if you have a large sample. Individual galaxy never is working, but if you have hundreds, it works. And that's what we have. We have 13,000. So we can do this kind of thing and assume it for a population. And then if you know your half-mass radius, then if you know lambda disk, actually you connect this to RV. This is very simple, trivially for an exponential disk. So if you know R1 half, you can work out the real radius. And as we also know the redshift, we get the real mass. And so we know the real mass for our population. What we now can do is we sample all our galaxies, take all the galaxies which have the same stellar mass, get the average real mass, and then see what the mass ratio is, and plot it as function of stellar mass. And that's something which we did. And here's basically the result. What I show you here is the half-mass radius of the disks. These are the red dots as function of the stellar mass, which is observed. And when you now look at the red dots, you see they follow beautifully a power law all the way to the large masses. And now what you can do is, of course, you can work out, if you believe in the Moster baryon fraction, you know what dark matter mass belongs to this M star, then you work out what the real radius would be. And if you know what lambda you have for the disk, it tells you what this disk scale length half-mass radius should be according to Moster. And then you see, indeed, this is this kind of dashed curve for the galaxies below the Milky Way. It follows very nicely the slope which we observed. So you recover the beta value of the rise, but then it begins to flare. And why does it flare? Simply because it's in a regime where the baryon fraction goes down. So you increase the stellar mass a little bit, but you increase the dark matter mass a lot. And if the disk radius is sensitive to the real radius, this also leads to a flaring then of the disk. And this is what you then expect here. But you see, it doesn't do this. All our 11,000 galaxies still happily continue this kind of beta slope to larger and larger baryon fraction. And so it's not only few galaxies, it's all kind of galaxies. By the way, when you look at ellipticals, which are the blue dots, then they show this flaring over there, but they do something rather strange here. And this is, okay, we didn't get to this, so this is something you can do if you want. So what you also can do is there's a lot of spread around this, and we said, okay, if this spread is due to delta lambda, that means this is the average lambda, and this the disk with larger rays have a little larger lambda, and those which smaller rays have smaller lambda. I get the lambda distribution of my 11,000 disk, and this is basically the result. From the observations, I get this lambda distribution by the solid curve. Theory gives me this log normal distribution. It works beautifully, maybe a little thicker, a little broader, but it also tells you that our theory works. So now this was for the galaxies between 1 and 1.5 in redshift. And it's already interesting that at high redshift we get the same trend, no change in the baryon fraction for spiral galaxies. But we can do it for different redshifts. And we always find this power law slope without any flaring, without any turning around, without any AGN feedback evidence in all of these redshift samples. But what changes is at the 0 point of R. And the reason is very simple. When you go to lower redshift galaxies, they live in the universe where the mean density is smaller, and so the real radii for given mass are a little larger, and therefore the disk radii are a little larger. And actually we can then see this directly in the 0 point, and actually we did work out a Hubble constant. You can do it, and it worked out to be what you would expect. And if you put it all then together, scale it to the same, if you take the redshift dependence out, then you get this kind of trend, and it beautifully leads to a power law of 0.8. Jon Boster gave this beta of 0.81, so we were very happy, and we said, okay, there are no baryon, no problems, and we reach baryon fractions of cosmic values at large masses. But what we then began to see when you put everything together is an increase in the slope at very large masses. And it turns out this is precisely what you would expect, because you cannot go on with baryon fraction increasing all the way to 10,000 compared to the cosmic baryon fraction. When you reach the cosmic baryon fraction, then the stellar mass must become proportional to the real mass and cannot increase anymore. And this leads exactly to this right over there. And we find that actually when we put all the data together, then this change to a constant happens at 0.1, not at 0.156 as you would expect for cosmic baryons. But this is if you take together also the galaxies at high redshift. When you look at the low redshift galaxies, then you are here, which is 0.15. So the baryon fraction where it levels off depends on redshift. And that's exactly what we expect, because when you go to higher redshift, look, we only look at the stellar mass. We miss the gas mass. And at high redshift, the gas is not negligible, and therefore the leveling off happens at a smaller baryon fraction than the cosmic baryon fraction. So this can all now be very well explained. The Milky Way sits somewhere here, and you see it's not at all special. You go to a larger spiral galaxies, and the baryon fraction is still increasing. There's nothing special to it, and the only question is, why is it so? And when I began thinking about this in Berkeley with Chris at a nice coffee, we thought, oh, this is dumb, this is so trivial, that we wondered why nobody really understood. Look, this turnaround is due to AGN feedback. But AGN feedback depends on the mass of a black hole. And the mass of the black hole correlates with the spheroid mass of a galaxy. And for an elliptical, the spheroid mass is the stellar mass. So you would expect if you have massive ellipticals, you have 10⁹ solar mass black hole, you get a lot of feedback. But for these galaxies, the spheroid mass is the bulge mass. And the bulge mass is tiny compared to the total stellar mass. Look at the Milky Way. And the Milky Way is almost 10⁻11 solar masses in stars, but the black hole is only a few 10⁶ solar masses, much smaller than 10⁸, what you would expect, simply because its bulge mass is small. And therefore, for spiral galaxies, AGN feedback does not simply work. It cannot. And you would, after the fact, we thought, oh, how dumb are we, not figuring it out, but it seems other people also didn't know. And so now this is basically my answer. If you now do your numerical simulations, when you look at galaxy properties and so on, please take into account that spirals don't show an AGN feedback process as you see in elliptical galaxies from now on. So that's all I wanted to say. Thanks very much.
Thank you, Andy. And I lose sleep these days because I worry about AI agents taking over science. But when listening to you, I don't think they will ever do something like you did. So creativity is still in the territory of humans.
Thanks for the compliment.
But the question I have is that redshift 0, we know like the most massive galaxies usually sit in galaxies or
in clusters.
The clusters of galaxies.
Mm-hmm.
And most of the baryons in those systems are in the hot gas. They are not in the stars. We know that because you look at clusters and most of the baryons are in the hot gas. So if you were to account for the hot gas, you shouldn't reach actually 16%.
The hot gas in the clusters, not bound to any galaxy in the clusters, is probably mostly dominated by the ellipticals and not maybe so much by mass loss from the spirals.
Hot gas in them.
Well, the very massive spirals in the cluster, this gets stripped anyway, and it becomes part of the whole.
Irrespective of where they are, you're saying that the stars, basically the star formation efficiency is 100%.
Yeah, it is close to 100%.
Which is very surprising. I mean,
I find it surprising too.
Yeah.
It's, let's say, not, 0.15 and 0.12 or so is what we get. So it's a little less than 100%, but it's close to 100, yeah.
Okay.
But it's just what comes out here.
That's surprising. Okay. 2 questions. Go ahead, Liam.
If you integrate over the halo mass function, what do you get for the total stellar fraction of baryons in the universe?
Yes, no, we didn't do it yet. The problem was, a week ago, I realized I have to give an ITC colloquium as usual. And I can't, after 15 years coming here, I can't always tell you the same. So I looked in my drawer what hasn't been published, and this came out, and so I prepared this. And now I realize I need to publish it. So it's not yet published, but you're absolutely right. It's a very good question. Also to look at the Schechter function just for the spirals itself, it will not show the turnaround. Cannot show the turnaround, which you see for all galaxies. Of course, the problem is when you go to the very massive galaxies, you're dominated by ellipticals, so you see this kind of cutoff. Yeah.
Go ahead.
At redshift 0, you have these 2 subclasses that you can test this with at the very extreme. The superspirals and giant whole surface brightness galaxies. Superspirals are relatively gas poor, like the normal gas fractions, while GLSBs, they're more like high redshift galaxies where you have more gas than stars, substantially more. So have you tried putting them here?
That's a good question. The question is, you need good statistics to do this kind of thing. Now you have thousands. So if there are only 5 or so, you can. 10 is a little poor on the statistic side, but it might be worth looking into this anyway. Good suggestion. Thanks very much.
And of course, Andy, if star formation efficiency is 100%, there should be high metallicity, of course, in those systems, because you keep having a lot of generations.
Sure.
Last comment, go ahead.
So how does the galaxy decide whether it's a disk or not at this high masses? Is it like process?
Well, in this, I would say whenever you see V rod over sigma larger than 1, this is how I decide whether it's a disk. How the galaxy decides whether it's a disk is just given by the dissipation of random motion in gas. So actually, any gas falling into a halo will always settle into a disk. The only problem is how you get a spheroid after the fact. Well, the disk is the most natural thing that happens. It's the lowest energy state for given angular momentum. So everything that loses energy will settle into a disk. And the massive galaxies form spheroids because you have the mergers going on. So actually, those who escape a merger, a major merger, should still be disks to some extent. Why not? I mean,
So there can be arbitrary massive disks here, or?
yeah, that's a very good question. If you reach cosmic baryon fracture, why should there be a cutoff? And why aren't there these disks going to even larger masses? Good question. I don't know. That's a good.
Yeah, super galaxies we call it.
Super galaxies.
Yeah,
Maybe
let's,
they are in the formation process right now. If you look, maybe you can find some. Maybe it takes time for them to form, and we might be in this phase right now.
Let's thank Andy again for
Right, yeah, thank you for having me here. Hi, I'm Jung-Tsung. I'm from Ohio State University. And today I'd like to talk about the gamma ray emission coming out from the sun and how it's important for understanding galactic cosmic ray and solar magnetic field. And this work is in collaboration with Mahbube Asghari, who's a scientist here, as well as with John Beacom and Annika Peter, who are the faculty at Ohio State University. Okay, so in the first slide, I like to start with something very simple to motivate the talk. So why is it interesting to understand the gamma ray emission coming out from the sun? And the reason is that the sun is actually hotter than what we think. So we know that the photosphere is about 6,000 Kelvin. That corresponds to the visible light, or 1 eV. Corona can get really hot through the wave-driven turbulence or reconnection events. But the temperature is maybe a few million Kelvin. So that corresponds to EUV or X-ray. Or in terms of energy, that's about 1 keV. Occasionally, there will be like big solar flares that produce a non-thermal particle, and then therefore the gamma ray coming out from there. But those energies usually few GeV, and also those events are very transient. That means that they can be taken out from the long-term gamma ray observational data. Now, surprisingly, the gamma ray observation also still see the continual GeV to TeV emission coming out from the sun. And now what do I mean by that? So Fermi, back in 2008 to 2010, has seen the gamma ray emission from 100 MeV all the way to 100 GeV. And here you can see that at the low energy part, below 100 GeV, they see a rather hot spectrum. The spectrum goes like energy to a minus 2.2. Recently, Hawk has announced the observation at about 1 TeV. And they somehow see a very soft spectrum that goes like energy to the minus 3.6. And if you look at this spectrum again, you will notice that during the solar minimum of the sun, we see a higher gamma ray fluxes. And during the solar max, or over the entire solar cycle, we see a lower gamma ray emission. And you can see that offset is about factor 2 to factor 3 across 4 order of magnitude, from 100 MeV all the way to 1 TeV. Okay? Now, we actually have some reasonable understanding about what is happening here. Such emission is caused by galactic cosmic ray proton and helium reaching the solar photosphere, in specific, the photosphere and the chromosphere. And it interacts with the solar gas there, which is mostly hydrogen and helium. And that creates a PP collision, and that PP collision produces a neutral pion, and neutral pion decay to the gamma rays. Okay? So that's a basic mechanism. But in order for those gamma rays to get out from the sun, to transmit out from the sun, the incoming proton has to be first reflected, and from inward to outward direction. And on the way out, they interact with the solar gas, and that produces a pion, and pion decay to 2 gamma. So the key factor here is those incoming galactic cosmic ray proton are reflected by the solar magnetic field at the photosphere layer. Okay. And one can ask, okay, exactly where does that happen? We want the PP interaction to happen, so that means the optical depth is about order of unity. That's the requirement. And very qualitatively, that tells us emission should happen somewhere between minus 1,000 kilometers to positive 1,000 kilometers. So that covers a little bit of a convection zone of the sun, the entire photosphere layer of the sun, and a little bit of the lower chromosphere. Basically, above 1,000 kilometers, the background density of the sun, the solar gas density of the sun is just too low to initiate the PP interaction in the first place. Below minus 1,000 kilometers, the particle will be absorbed before anything can happen, so nothing interesting there. So there's actually a very sweet spot here. Okay. Now, what happened at that height? So here you are seeing the popcorn-like structure. Each pattern is a convection cell, and it's about the size of a Texas. So maybe the horizontal size is about 1,500 kilometers. Vertical height is about 1/3 of that, so that's about 500 kilometers. Okay? So what you're seeing here is a hot plasma boiling up, and it reach the top and move to the side and sink down. And reach again, go to up, move to the side and sink down. That's one bright cell we are seeing here. And each bright cell is a convection cell. But there are magnetic fields at the photosphere layer. And what would happen to a magnetic field in such an environment? Such work was pioneered by late Nigel Weiss back in 1966. Here you can see that understanding it as like a convection cell in the beginning, and you can impose a, say, initially homogeneous magnetic field. But the field is frozen in the plasma. So wherever the fluid goes, the field goes with it. And therefore, the eddy, the convection, is going to drag and fold magnetic field at the edge of the eddy. Okay? And those fields, they can reconnect and become a high-intensity region. And what's interesting here is that after the system saturated, at the center of the cell, you don't get any magnetic field. All the magnetic field has been expelled to the edge of the cell. And therefore, you start from a homogeneous field distribution. In the end, you got very filamentary field distribution at the photosphere layer. So having that in mind, what do we actually know about the more realistic open magnetic field in the photosphere, chromosphere, and corona? And such work, it's actually this plot is partially pioneered by the late Ed van Barloghen, who was a staff scientist here. We start from the bottom plot where you got the larger scale. You have a inverted wine bottle-like structure, which is this is called a network field. And between the network region, you have many convection cells. And each convection cell is going to drive those filamentary structures that I showed in the earlier plots. Okay? And in each of these big wine bottle-like structure, the network field, you got at the bottom of it is called a network element. Okay? And each network element is made by about 100 smaller inverted wine bottle-like structure. Okay? So this is called a flux tube. And this flux tube is a fundamental element of such a structure. But those flux tubes, they are embedded in those convection region. And those convection cells is going to move randomly. And that is going to drive the bottom of the flux tube. And that's going to drive the magnetic field and oscillate the alpha wave upward. Alpha waves, some of them got reflected as they propagate out. And whenever you have a two counter-streaming alpha wave, they are going to cascade and produce a smaller scale magnetic turbulence. So here we are seeing a multiple structure. We got a bigger structure, the network field. We got a smaller structure, the flux tube, and also the small scale canopies here. And at the smallest scale, we got the alpha wave turbulence cascade. So multi-scale magnetic structure here. What does that do? What do all this structure do to the incoming charged particle, the incoming galactic cosmic ray? So here I'm showing you a schematic diagram for the particle coming in. If there were no turbulence, the particle would still get reflected through the magnetic bottle effect. Basically, the particle got squeezed out from this inverted wine bottle-like structure. Okay. But now there is a background alpha wave turbulence, and that perturbed the incoming charged particles. So particle got scatter randomly. And what we find out is that whenever you have the turbulence, particles tend to be got scattered a little bit higher, and where the background density is lower. And therefore, you expect that whenever there's turbulence, the eventual gamma ray emission is going to be slightly lower. So here I'm going to show you our results. So here I studied 5 field lines, 4 coming out from the quieter region of the sun, 1 coming out from the very active region of the sun. Okay? And this is our predictive results. So you can see that from field line to field line 4, which correspond to the quieter region of the sun, our result, while the overall magnitude is out by the data by about factor 2, the spectral slope somehow agree quite well with the data. Okay, we got very hot spectrum at a low energy and very soft spectrum, which is also minus 3.6. That agree with the Hawk very well. Okay. And you can see that for the active region, the spectrum is very hard, and it goes like energy to the minus 2.7. And some of you may actually know what does 2.7 means in the cosmic physics. That is actually the spectrum of the incoming cosmic proton. So you can see that our results actually agree with the data of a gamma ray data, but we do not get such a weird result that from the incoming proton. Here's a conclusion slide. One line takeaway is that it's those convection-driven filamentary structure that determine the eventual gamma ray data that we see from Fermi and Hawk. Okay? And of course, one can use the more advanced magneto-convection simulation packages to study those photosphere magnetic field and understand what is really going on to the gamma ray emission. And the reason we want to do this is because we would like to use the solar gamma ray to, in the future, probe the galactic cosmic proton and helium transport in the photosphere and chromosphere and maybe the coronal region, where the space probe can never reach. And there's another interesting aspect which I have no time to talk about here, is the solar halo emission. It's basically coming out from the electron interaction with the solar photon that produce inverse content. And that's also a powerful tool to understand the particle transport in the inner heliosphere. Okay, thank you.
Thank you, Jung-Tsung. And in fact, this was a puzzle for explaining the behavior with solar minimum and maximum was a puzzle that some people thought maybe it indicates new physics, but you explain it with known physics, so thank you.
Oh yeah, some people think such emission may come out from like dark matter annihilation at the center of the sun. That will require many fine-tuning, and what we show here is that with a very standard solar physics and astrophysics modeling, one can get this result that fit well with the data. Yes.
Great, thank you. Any questions, comments? Oh, that's a compliment. You made everything very clear.
Yeah.
Thank you so much.
Yeah, thank you.
Hi everyone, I'm Roger. I'm from down the street from the CTP, and today I'd love to talk a bit more about high-redshift cosmology and how we can use the Lyman-alpha forest and why astrophysics and cosmology start to talk to each other in that regime. And this is some recent work we've been doing with a few of my collaborators, Misha, Jamie, Stephen, and Boriana, who was also here for quite some time, and I'm very glad to be here today. So first of all, a little bit of high-level introduction. So what is the Lyman-alpha forest? On the previous slide, you saw a rendering of the intergalactic medium. And what we're observing is a high-redshift quasar between roughly redshift 2 and 5 that emits a lot of light. And then these photons, when they travel to us, they're absorbed by the neutral hydrogen along the way. And that is this little spiky structure that you see on this plot. And you do that at lower redshift, you have a few of these spikes, you do that at higher redshift, and the entire forest is almost depleted. And the wonderful idea about the Lyman-alpha forest is that it was dreamt up by observers and theorists more than 30 years ago, because you had an extremely fine 1D mapping of the neutral hydrogen in the universe. So you could go to very small scales. which you couldn't do with galaxies, for example. And you still can't do with galaxies. And that's kind of the strength of this probe. And now with SDSS and the currently observing dark energy spectroscopic instrument, we have many of these different Lyman-alpha forests that you can cross-correlate with each other, meaning you don't only have a trace at very small scales, but you can cover an entire range of scales. Very schematically, this is shown here on this plot, where we have the scales from very large scales on the bottom left to very small scales on the right-hand side. And you see that the Lyman-alpha forest sits pretty much in the middle compared to all the other traces that we have. So we have low redshift galaxies that trace very large scales. We have CMB lensing, which are the CMB photons coming from the CMB, but are then deflected due to all the intervening matter along the line of sight. And the Lyman-alpha forest that sits exactly in the middle. And this is a pretty unique probe of high redshift, small scales. And you get most of the leading constraints on neutrino mass, warm dark matter models, primordial black holes from the Lyman-alpha forest. But these constraints are by now almost 20 years old, and they're still state-of-the-art. And for DESI, this is one of the high redshift anchors that DESI is using. So now you might want to ask, why does DESI even need another probe? And this is shown in this plot, which basically captures the BAO physics, so the key driver of what DESI is trying to measure. So here you see the energy density as a function of scale. And starting from low redshift, you see this contour that is basically vertical. And the higher redshift you go, the more you see a rotation going from a dark energy-dominated universe to a matter-dominated universe that is probed by the Lyman-alpha forest. So you use that in order to break degeneracies. But how do we actually get information out of the Lyman-alpha forest? You saw these extremely jiggly lines that I showed you earlier. And what people have done for this, also pioneered here within Harvard, is to use hydro simulations because we understand the physics quite well of the Lyman-alpha forest. And this is shown here at the top. So you use some sort of linear theory prescription and then say, I take an ansatz from a hydro simulation, and this should be roughly the physics, how the Lyman-alpha forest should behave on intermediate to small scales. But it turns out that this was very, very successful in giving us first constraints on astrophysical, like warm dark matter models, but also cosmological, beyond standard model things like the neutrino mass. But we're hitting the end of the line here. And what we set out to do was the question, how can we extract more information from the Lyman-alpha forest? Because if you can extract smaller scale information, that means basically DESI is becoming DESI times 2 because you can extract a larger volume. So you get a free survey within the survey you have at the moment. So what we set out doing is using an effective field theory of large-scale structure approach, meaning you have the linear theory approach here, and then you use all the symmetry-based operators that would be allowed by the tracer that you're looking at. I'm not going to go into these details, but the interesting thing is you can solve all these problems that I have briefly outlined here at the top. There's some sort of BAO shift that has been seen in the linear theory modeling of the Lyman-alpha forest. We can now forward model this. Does that mean that this is a theory of everything as far as the forest is concerned? So would that mean that we can actually replace hydro simulations? So we don't need to run a simulation, we just need a pen and paper and solve a few equations. And that's what I want to talk about today. So here in the top row, you see the Lyman-alpha forest field, and in the bottom row, you see the halo field. So halos are proxies for high redshift galaxies. And the first column is just a slice through a hydro simulations for both of these fields, for Lyman-alphas and for halos. And the center column is taking this model that I've just shown you, using the same initial condition as that simulation and forward evolving all of these initial conditions. So it's a purely analytic way of solving a simulation. So instead of doing everything within a few weeks, a few petabytes of storage, you do everything on this laptop in 30 seconds. And what you get out of it is something that by eye looks fairly good. Obviously, you could say, okay, this sounds too good to be true. Let's dig a bit deeper. So first of all, what does that mean for the power spectrum? So here, left-hand side is the current theory modeling of the Lyman-alpha forest. The black lines is the measurement on that simulation, and the blue line is the theory modeling that we have. And on the right-hand side, the same thing, just the red line is being the theory modeling that we do. And you see that basically this theory modeling that we had so far fails on all scales. So you can't even recover the larger scales that have always been assumed to be fairly linear. And it turns out that they're quite more nonlinear than we assumed they would be, although the Lyman-alpha forest is at very high redshift, where you have access to more quasi-linear modes. And things become a bit more cleaner here when using a cubic model, for example. That again means you can suddenly extract scales up to almost k of a half, which would correspond to a survey volume of a factor of 3 to 5 larger than what we currently have. And that then again translates into a factor of a few smaller error bars on the key cosmological parameters. But another side effect of this is people always say we need bigger, better, stronger simulations. And I partially agree with this. On one hand, we do need better simulations, and there's a remarkable effort going on here, but we don't necessarily need bigger simulations. We just need to resolve the small-scale physics as done in these little boxes. So this is the Sherwood simulation, and this is the illustrious TNG simulation. And then we can use this procedure and blow this up to cosmological volumes. So suddenly we can have the physics informed by a Hydra simulation blown up to a few gigaparsecs, or even 10 gigaparsec if you want to cover the entire DESI volume. And this is the approach that we're doing at the moment to bring the Lyman-alpha forest under theoretical control so that we can extract more information from the Lyman-alpha forest, but also then go the other way around. How do we use that information to create simulations for high redshift constraints? For example, DESI-2, the successor of DESI, is supposed to measure many Lyman-alpha forests, but also high redshift quasars, Lyman-alpha emitters, and Lyman break galaxies. And how to cross-correlate these and have a good understanding of the systematics, of the theory challenges that we have. For that, we need simulations. So if there's just a single thing that I want you to take away from today, is the Lyman-alpha forest is a pristine high redshift tracer, and that means you can cover a very wide range of scales, which in the cosmology we usually denote by K. So we'll have a purely math symmetry-based expansion, so a Taylor expansion of the field of the Lyman forest itself, and that means we can suddenly simulate the entire forest calibrated on a set of Hydra simulation. And this is something now within DESI that we're trying to analyze and see how much more information we can extract from the data. And that opens a few cute new possibilities, starting from covariance matrix estimation to EFT emulators, simulation-based priors, or even field-level inference, where people ask the question, how can we extract all of the information that is stored in the data, and not just a subset of the summary statistics? And that's what I want to leave with you today. Thank you very much, and happy to take any questions.
So indeed, Roger, we will have 3D maps of the hydrogen, not just the tensor beams in the future, and that offers an opportunity to learn not just about the power spectrum, which is a two-point statistic, but much more than that. But you work in theory land, and how do you know that you converge? Because you have a limited resolution in your... So are you trying different resolutions? How do you know that you have the correct answer?
That's a good question. So what we did so far in this approach, what I showed you today, is on a single simulation. We tested this on a different suites of Hydra simulations that are completely independent implementations, different physics, different resolution effects, different number of particles, and the results are robust with respect to that. And coming from theory land, as you said, this is because we can smooth out the very small scales or integrate those out. So we don't really care exactly what the baryonic feedback would be or what the exact implementation would be, but we can capture that in the model. So on large scales, this would work to some degree until it breaks down here, where roughly this theory land model cannot capture all the physics that are there. So as you said, we still need the Hydra simulations, but now we can stitch together two different worlds.
Any comments, questions? If not, let's thank Roger again.
I think so. Yeah. Can you hear me?
Yeah, okay, great. Yeah, so thanks a lot for having me here. My name is Natan de Isídio. I'm a PhD candidate at ESO, the European Sovereign Observatory in Garching, Munich. And today I'm going to talk about this paper that came out on arXiv last week, and it got accepted last week as well, which the title is The Kinematic Imprinting of Environmental Quenching in Nearby Galaxies. So we know that galaxies are formed out of cold dark matter halos that collapse from the ambient background, and then there is a very complex interplay of different processes that shape these galaxies throughout cosmic time. Something that I really want to say is that if you want to get a very unbiased view of what's shaping these galaxies, you have to take into account many different wavelengths. And we know that galaxies quench. And here I'm going to say that a galaxy is dead when it's fully quenched, so it's not actively forming new stars. And there are two main categories to quench a galaxy. So the first one is inside-out quenching, which is basically feedback from high-mass stars and also supermassive black holes. So as you can see in this TNG simulation, you have here at some point when the AGN is activated, these bubbles that can either heat up the gas, preventing it from cooling, or directly eject the gas out of the galaxy. But what I want to focus in this presentation is the environmental mechanisms, basically. So environmental mechanisms are basically when the environment is shaping these galaxies. So you have tidal interactions, you have galaxy-galaxy mergers, for example, but you can also have gas stripping. So here I'm showing this very famous case of a galaxy that has these tails. This is a jellyfish galaxy, so you can see ionized gas, but you can also see molecular gas, so there is stars forming out of this gas. But you also have hot gas here. But perhaps the most important environmental mechanism that I'm going to talk about today is this one, starvation or strangulation. We know that galaxies have a hot gas reservoir surrounding them, and you also know that at some point, eventually this hot gas will cool down and feed starvation in the disk. However, when a satellite galaxy or a galaxy falls into a more massive halo, this galaxy might lose the ownership of its own hot gas. And then there is no gas replenishment, and then the galaxy will quench after a long time scale. And my takeaway here is that, so I made this scheme just to say that all these quenching processes are gonna leave distinct imprints in the kinematics of these galaxies. So as you can see here in the rotation curve. So if the galaxies are interacting very close, you're gonna see this in the kinematics as well. If there is an AGN, the gauges component is gonna be affected, and so on. So as I said before, what we want to understand is basically how these asymmetries in the kinematics can tell us about the quenching mechanisms that are driving them, but we also want to know how often these processes, these different processes occur, and the relative role of them. And here in this PhD, what I'm doing is basically to look at optical, radio, X-rays, simulations, Colibri, and TNG50. And there is also infrared data coming out soon from this large survey that is going to run for the next 5 years on VLT in Chile, led by my supervisor, Paulo Papesso. So the optical data come from the MANGA survey, which is a spectroscopic survey. And there is around 10,000 galaxies. So it's very convenient because you have a corresponding spectrum for each spaxel or pixel in these galaxies. So we have the stellar velocity maps, we also have the gauges velocity maps, and you can see this spatially resolved information. And the cold gas information come from the Very Large Array and Green Bank Telescope. So this is basically an animated figure that I made for my undergrad paper 2 years ago, in which you can see basically the atomic hydrogen emission. So sample selection, there is a lot of things happening here, but what I want to say with this slide is basically that we have a very high signal-to-noise ratio for the data. So with high, I mean over 5. And also I want to say that our sample is representative of the local galaxies. So here I'm showing the comparison with SDSS, so in terms of stellar mass, in terms of halo mass, and here in terms of environment, whether the galaxy is a satellite or a central. And we are covering a very broad range in terms of stellar mass, star formation rate, and also morphologies. The main method of this work is the kinemetry package. So kinemetry is a tool that basically models the kinematics of these galaxies. And I apply this criterion here, which is a function of different coefficients. This K1 here basically is telling us about the rotating component of these galaxies. And all the higher coefficients basically tell how disturbed these galaxies are. So here I'm showing two different examples of very symmetric galaxies in terms of gas, and here stars. But we also have very disturbed galaxies, so what's happening there? And here I want to highlight this galaxy here. It was one of the referee comments. So the referee was concerned about this emission in the outskirts because they were a bit concerned if whether this emission is genuine from the galaxy or not. And this is an AGN. So what we are seeing here is basically the AGN. Sorry. Yeah, the AGN outflows, so the feedback. So we split our results into 6 cases. I'm not going to the details about all of them because I don't have much time. But what I want to say is that basically we separate these galaxies based on the symmetries that we see in the kinematics. So we have symmetric galaxies that are star forming. We also have symmetric galaxies in the stellar component, but asymmetric in the gauges component, so what's happening there. So we also developed this algorithm to calculate the projected separation of these galaxies, projected distance to the nearest neighbor, and we take into account not only the projected separation, but also the line of sight velocity difference, just to make sure that these galaxies are interacting. So the first case is symmetric subforming galaxies. So basically, our conclusion with this is that these galaxies are evolving through secular evolution with no strong environmental effects happening there. This case 3 already, I'm showing symmetric galaxies in the stellar component, but the gauges component is disturbed somehow. So what's happening there? And that would be due to AGN outflows, for example. We don't expect the AGN to affect the stellar kinematics, but it definitely does affect the gauges kinematics, right? So we basically analyze a broad component around these AGN emission galaxies. And the conclusion here is basically that we don't have many AGNs, which is also expected because in the local universe we don't have very a high number of AGN galaxies. So the conclusion with this one is basically that there are a lot of galaxy-galaxy interactions, but this is important. I'm not saying that this galaxy never had an AGN before, right? So the AGN might be very important and relevant, but in a different stage. And the last case, and the most important one, is galaxies with symmetric stellar kinematics. So they are very well rotating, but there are some problems because these galaxies are quenched. They are well rotating. They don't have any kind of gas. So very low H1 gas mass fraction, no ionized gas at all. So what's happening there to quench these galaxies? And the way we interpret these galaxies is basically this one. So we have this galaxy that's going to fall into a more massive halo, and at some point, this satellite galaxy will lose the hot gas reservoir, and then the galaxy will keep forming new stars for a long time, for a long period. But after a few giga-years, these galaxies are going to quench because there's no gas replenishment, basically. And this is the case of most of the satellite galaxies that we have in our sample. And yeah, basically the conclusion here is that the hot gas reservoir of the satellites is stripped, leaving the satellite with no gas replenishment and quenching over long time scales. This is the last plot of this paper that I want to show, which is basically a mass match analysis. So here I'm showing the sizes of these 4 different populations of galaxies. So we have symmetric satellites, asymmetric satellites, symmetric centrals, and asymmetric centrals. And as you can see here, I draw your attention for this population, which is the most quenched galaxies among the quenched population, and they are also the most compact subpopulation here. So what's happening in these galaxies that not only affect the gas component, but also the sizes of these galaxies. And the way we see it is, and please go and come talk to me if you have any questions, concerns, or anything about this, is that these galaxies are starved, so they face a very long period of starvation. And they had a strong history of gas stripping or material stripping in general. So basically, the galaxy falls into a more massive halo, and then there is this gas stripping in the outer layer of the disk, and eventually even the star starts to be removed, and then the end product that we see is basically bulge-like structure, so super compact and quaint galaxies. I thought I would have more time just to go into the details in this, but basically it's the project that I'm working on right now, which is based on TNG and Colibri simulations. With simulations, we can basically follow the whole evolution of these galaxies. And this is a very nice plot that I'm having right now, which is basically, I developed this algorithm to calculate the info times of these galaxies. And as you can see, I'm showing here the hot gas of these galaxies now and at infall. So how much hot gas these galaxies lost upon infall. And there is a very, very clear correlation here, at least the way I see it, with the look-back time at infall. And this is something that it's quite interesting and also no one has done before. So yeah, if you are interested, please come talk to me. I'm going to leave you with my takeaway. And again, thanks a lot for having me here.
Very interesting, Natan. And you're graduating soon?
I'm a second year PhD student at
second,
ISO.
so you've done
Yeah,
a lot
I
of
just
work?
started the second year,
Uh-huh.
but out of 3. So
Okay.
at ISO we have 3, so basically I'm also thinking about applying soon.
Good luck. You did the wonderful work so far. Any questions, comments? Yes?
So what's the mechanism of stripping the gas? Do you imply that ramp pressure works for these small halos?
Yes, so I think this is a very good question because we consider all the quenching mechanisms, ramp pressure stripping, tidal interactions, galaxy harassment, agent feedback, starvation, as equally possible. And for ramp pressure stripping in particular, I have one plot here. Ramp pressure stripping in particular, there is this galaxy here, and there is a specific section of the paper that talks about measuring ramp pressure tails in these galaxies in MANGA, because MANGA has a very compact field of view compared to like MUSE, for example, at ISO. And the conclusion is that we can measure the asymmetries in the gauges component. However, we cannot see the tails, but somehow we can still measure there because the internal structure of this gas is still affected. Not as much as it would be like seeing the whole galaxy, but we can still measure.
Okay, we had a very long lunch today and very informative, so thank you to all the speakers.